Greetings everyone. Today in this video, I will be presenting our research paper called SegNet, a segmented machine learning approach for drones wildfire detection. Let me start off by introducing myself. My name is Aditya Jonnalagadda. I'm an engineering student at Carleton University at the Department of Mechanical and Aerospace Engineering. This research was conducted under the supervision of Professor Hashim. He is a professor and research supervisor for this project from the Department of Mechanical and Aerospace Engineering from Carleton University as well. Let us start off by having a brief introduction to this paper. Our dependence on forest resources is crucial to our daily lives. Often referred to as the planet's lungs, forests play a vital role in filtering air, releasing oxygen, and then reducing the carbon dioxide levels in the air. Beyond this, they serve as habitats for diverse animals, act as windbreaks for crops, and effectively purify water from pollution-causing agents. The economic impact is significant, creating jobs and enhancing revenues for countries. Forests offer essential ecosystem services by purifying air, regulating climate, protecting against natural disasters, and supporting biodiversity. They provide resources such as timber, medicine, contribute to recreation, and preserve cultural heritage. Looking at the forest share of global forest area from 2020, Europe, South America, North America, Africa, and Asia, all these contribute to the same amounts of land mass. However, the escalating frequency and intensity of forest fires, exacerbated by climate change and human activities, have profound consequences on ecosystems, communities, and the environment. Ecologically, forest fires destroy vital habitats, decimate wildlife populations, and disrupt ecosystems. Recovering from such devastation is challenging for native flora and fauna, with invasive species often taking hold. The following figure displays a global tree cover loss from 2001 to 2022. With red dots indicating areas affected by forest fires, some of which are currently under restoration efforts. Communities residing near these forests face immediate peril. With lives and homes in jeopardy, firefighters bravely risk their lives battling these infernos. Smoke and air pollution pose serious health threats, particularly impacting vulnerable populations. Evacuations disrupt livelihoods and inflict psychological trauma. The economic toll is staggering, with soaring firefighting expenditures and losses in timber, agriculture, and tourism industries. The long-term consequences include diminished soil fertility, hindering agricultural and reduced water quality, affecting downstream communities. Looking at the wildfire instances across the globe, in Canada alone, over 8,000 fires annually consume an average of more than 2.1 million hectares. In the western US, wildfire frequency and burnt areas have surged by 400% over the past decade. The devastating 2020 Australian wildfire that we all remember claimed over 1,500 homes and 500,000 animal lives, burned more than 14 million acres of land. Other destructive wildfires like the 2018 California fire and the 2019 Amazon rainforest fire resulted in substantial losses as well. And thus, certain conventional solutions were brought up by researchers and engineers and scientists all around the globe. These conventional solutions mostly consisted of traditional wildfire detectors utilizing gas, smoke, temperature, and flame sensors. But these have a limitation. These limitations are such as slow response times and restricted coverage areas. But then the researchers moved forward and brought up newer solutions such as the static vision surveillance. These were in the form of watchtowers, in the form of security personnel moving throughout the forest. But then these are not economically viable because static vision surveillance, like the watchtowers, cannot be implemented at each and every interval inside a huge forest. These had a large but fixed coverage area, which makes it much more difficult for detecting wildfires away from those towers. And then when we look at the early wildfire detection, then it also becomes difficult to detect early wildfire detection due to the canopies that are formed due to the forests. The conventional solutions have turned into modern solutions where researchers and scientists and engineers have brought recent advancements into cutting-edge computer vision approaches, including infrared images, especially in UAV or drone systems. These systems, coupled with deep learning methods, exhibit remarkable progress in detecting and combating deep forest wildfires. Deep learning-based fire detection algorithms analyze the color and geometric characteristics of wildfires, feeding their findings into fire propagation models. Let us look at some of the important obstacles we must overcome. The first one is the importance of space and time resolutions in wildfire detection. Effective real-time wildfire detection algorithms require a careful balance between space and time resolutions. Stationary imagery, as seen in satellite or watchtower observations, excels in time resolution but suffers from low spatial resolution. This is because the incorporation of heavy, high-performance GPUs in these platforms enables faster processing, reducing overall processing times. However, challenges arise from light dispersion, diverse angles, pixel information, and environmental factors like fog and cloud cover, limiting spatial resolution. On the other hand, mobile imagery such as drone or rover observations provides excellent spatial resolution but lags in time resolution. Conventional fire detection methods like smoke and temperature sensors are not practically effective in real-time scenarios with these platforms. Researchers encounter various limitations in this domain, impacting the smooth progression of their studies. Several obstacles hinder progress in real-time wildfire detection algorithms. Notably, the choice of graphics processing units present a challenge. High-powered GPUs, while enhancing processing speed, are impractical for drones due to their weight and volume. Another overlooked limitation pertains to detecting forest fires during the fall season, when certain trees change color, rendering pixel color-based image classification techniques ineffective and increasing the likelihood of false alarms. And then when we look at optimizing deep learning networks for real-time applications, in the realm of deep learning networks, the density of the network directly affects the delay in perceiving and classifying images. A denser neural network generally improves prediction accuracy by processing a richer feature pool. However, for real-time applications, algorithms must balance accuracy with processing speed, necessitating fewer dense layers. The challenge lies in achieving this without compromising accuracy, though. It is very important to understand that accuracy shall not be compromised when we are looking at the processing speeds. Then comes the dataset challenges in wildfire detection. A significant gap in wildfire detection research is due to the limited availability of wildfire image datasets. With a scarcity of resources on the internet and restrictions on capturing real-life drone footage, researchers face challenges in obtaining diverse datasets for training and testing. To address this, though, researchers explore augmenting datasets with synthetic images generated using generative adversarial networks. These modified images, often in YOLO v3 format, aid in localization and bounding box coordinates for fires. However, challenges arise in capturing diverse data from wildfire videos, as flames and smoke are amorphous and difficult to label. Annotating each image requires a substantial time, limiting the application of algorithms like YOLO v3 or faster RCNN due to the lack of labeled and formatted data. Let us go forward and look at the comparative studies did by fellow researchers in the field of AI/ML for wildfire detection. Adab in 2017 conducted a comparison research using artificial neural networks and local regression to map fire susceptibility. The findings concluded that ANN outperformed local regression. Leuenberger et al. Leuenberger in 2017 compared a deterministic approach with two machine learning techniques, random forest and extreme learning machine, revealing that all three techniques performed equally well, highlighting the advantage of data-driven, stochastic methods independent of prior information. Ingok Thatch in 2018 evaluated support vector machine, RF, and multilayer perceptron, with MLP achieving the highest accuracy score in wildfire risk prediction. Whereas Youssefi in 2020 employed generalized linear model, SVM, and functional discriminant analysis for multi-hazard modeling, the GLM demonstrating the best results in predicting wildfire risk. Escandri mapped fire susceptibility using general additive model, multivariate adaptive regression spline, SVM, and an ensemble of GAM, MARS, and SVM, showing SVM as the least accurate and the ensemble as the most predictive. Most research in wildfire modeling has focused on convolutional neural networks and its variants, including SSD, UNIT, and DeepLab. These approaches leverage the power of deep learning for improved accuracy and performance. Lesser known but effective learning algorithms include long short-term memory, deep belief network, and generative adversarial networks. However, these algorithms face limitations due to their hardware requirements, making them less suitable for mobile unmanned aerial vehicles. Let us now talk about the introduction to AI advancements and challenges in integrating AI into robotics engineering, especially in drones. The rapid evolution of artificial intelligence has positioned it as one of the most dynamic fields in applied science. However, as researchers endeavor to replicate the complexities of human brain, they have developed highly sophisticated algorithms that pose unique challenges, particularly in their integration to the engineering sector. In the domain of robotics engineering, the challenges become pronounced. A major obstacle arises from the complexity of machine learning models, demanding robust computational processing. The current technological landscape grapples with a critical limitation: the absence of powerful yet lightweight processing systems suitable for seamless integration into mobile robots such as drones or rovers. Equipping these autonomous devices with hefty, powerful processors is impractical due to their weight, impacting mobility and energy efficiency of the drone. Moreover, the cost factor further complicates the issue, making these potent processing systems economically unviable for mass production. This challenge becomes especially critical in the context of wildfire detection over extensive land masses. Applying complex machine learning algorithms on relatively weaker processors exacerbates the problem. This challenge becomes especially critical in the context of wildfire detection over extensive land masses. This is because we do not have one single drone to cover all of the forest. Rather, we have thousands of drones synchronized with each other, providing information in a real time. While opting for less powerful processors to address weight concerns, the computational time required for running intricate algorithms becomes significant, rendering these processors ineffective in real-time applications. And thus, there is a pressing need for novel approach in machine learning, one that can provide real-time decision-making capabilities in drone wildfire detection. Researchers are exploring innovative solutions to bridge the gap between algorithm robustness and the limitations of current processing technologies. This emphasis on efficiency and timeliness underscores the urgency in developing effective wildfire detection systems. In this paper, we address the problem of time resolution for UAV drone imagery, along with limited dataset available on wildfires around the world, using a segmented selection approach reducing the total feature map. This paper contributes the following to robotic wildfire surveillance systems: increased processing speeds, enabling real-time detection capabilities for wildfire, increased detection accuracies for wildfire, improved detection capabilities of early wildfire, and proposing a new direction for image classification of amorphous objects like fire, water, smoke, and etc. Moving on forward, let us talk about the dataset and preparation. Addressing the classification challenge of wildfire detection encounters data limitations, primarily stemming from the availability and proper labeling of classes. Unlike applications such as weather forecasting or stock market predictions, where data sets are relatively abundant, the realm of wildfire detection lacks a comprehensive dataset. Researchers highlight this shortfall, emphasizing the constraint it imposes on employing state-of-the-art techniques. Models like YOLO v3 and RCNN rely on training datasets with predefined bounding boxes around the target class, presenting a challenge in the context of wildfires due to the scarcity of such datasets. To overcome these limitations, this research adopts a novel approach, utilizing a custom dataset for model training. This dataset includes both complete images and segmented images, with each complete image further broken down into 12 segmented images. I'll be explaining about these complete and segmented images further in the video. Recognizing the importance of downsizing, the complete images are resized from 1280 into 720 pixels to 320 by 240 pixels using the Pillow library in the Python environment. This amalgamation of complete and the segmented images enables the model to recognize flame features both in comprehensive and partial representations, offering a more robust training ground for effective wildfire detection. In the following figure, you can see two separate sections, one with complete wildfire image and the other with segmented wildfire image. This complete wildfire image is broken down into 12 different segmented wildfire images, where the fire seen across different spots on the image is both represented as comprehensive on the left side as well as the partial representation on the right side. In the pursuit of refining wildfire detection models, challenges emerge from certain images within the dataset that counter the intended focus of the research. The objective is to guide the model in recognizing specific fire features like smoke, amorphous fire shapes, color, and brightness. However, some images introduce environmental factors such as fog and mist, potentially leading to misrepresentation of the model. This misrepresentation can result in false positives during the testing phase. Additionally, images captured during the fall season pose a unique challenge. This is because of the autumn coloring of trees. Shades of orange, red, and maroon resemble the colors of flames. When you look at the image shown on the left hand side of this slide, you can see that the fog can be misclassified as smoke caused by wildfire by the model. On the right hand side, you could see the red trees in the forest that could yield undesired false results by model due to misclassification of the red spots as fire spots in the image. Thus it is very important to clean data set before training the model. Next, coming on to the data augmentation. The augmentation process played a vital role in tackling real-world complexities embedded within the dataset, such as varying light conditions, different viewpoints, and external noise. Common scenarios during different seasons, techniques including rotation, translation, scaling, brightness adjustment, and the introduction of Gaussian noise were strategically applied. These methods collectively fortified the model's adaptability, enabling it to navigate through various input scenarios with resilience and precision. Rotation and translation provided variations in the orientation and position of fire-related features, mimicking real-world scenarios where fire instances may vary in appearance. Scaling allowed the model to adapt to different sizes of flames, a crucial factor in detecting fires at various distances. Brightness adjustment simulated the impact of changing lighting conditions, ensuring the model's robustness under different environmental settings, and introducing Gaussian noise replicated the presence of external factors that could affect image quality, reinforcing the model's ability to handle real-world noise effectively. By incorporating these augmentation strategies, the model not only became adept at handling diverse and nuanced data, but also emerged as a robust tool for subsequent analysis and predictions. The dataset enriched through these interventions provided a solid foundation for the model to generalize patterns effectively, ensuring its applicability in real-world situations. In the following slide, we can look at the dataset. This dataset comprises of original complete images, augmented complete images, and then the segmented images. All the number of images are shown in this particular table. Moving on forward with the methodology, conventional neural networks have always been popular for solving image classification problems because they use various filters to find features in an image. Feature extraction and engineering, which are vital parts of deep learning, have gained attention recently, but there's still much to learn in this area. This paper introduces a new way of reducing features in an image, which is essential for fire detection algorithms, especially when dealing with live image feeds. In fire detection, using live video, many features can't be assessed effectively due to constant flickering and moving pixels. Although this method is quick, it lacks in time resolution. This paper focuses on image feeds rather than video, aiming to improve the processing times for real-time detection. While the field of image classification has advanced in improving accuracy, little attention has been given to speeding up processing times. The algorithm in this paper aims to reduce the number of features in an input image through segmentation. When an image is fed into a neural network, especially a CNN, it contains numerous features, including objects and the environment. These features can be further divided based on distinctions like shape, color, texture of the object, or how the object interacts with the environment. Convolutional filters in neural networks produce features, and the collection of these features is called a feature map. More pixels in an image mean more information, resulting in a higher number of features. The choice of number of features in a feature map depends on the engineering problem at hand. For example, detecting defects in mechanical parts might require a high number of features to distinguish between different types of defects. In the case of wildfire detection, a larger feature map helps capture the fire and its characteristics, but can negatively impact the training stage. A larger feature map needs a larger dataset with highly varied fire and non-fire images, which is hard to find. If the dataset is not sufficient, training the algorithm with a larger feature map leads to underfitting, where the model doesn't learn well. Data augmentation techniques also don't work well, often leading to overfitting in these cases. Researchers often use smaller images like 256 by 256 pixels, resulting in a significantly smaller feature map. However, this comes at a cost, loss of information. Balancing the number of features in the feature map is crucial for effective wildfire detection, ensuring that the model learns well without being overwhelmed by too many or too few of a feature. The algorithm proposed in this paper seeks to strike this balance and improve the efficiency of wildfire detection from image feeds in real-time scenarios. Two different pixel sizes of the same shot of wildfire are taken for comparison. An image with 320 by 240 pixels on the left and an image with 1280 by 720 pixels on the right. Same segments of these images are extracted, which have the same area covered. Let's have a look at the information they provide. On the image on the left, which is 320 by 240 pixels, has 3 channels RGB, and thus in total the complete image is depicted by 230,400 elements, whereas the picture on the right has 2,764,800 elements that depicts that picture on the right. So the difference in elements that depict these images show us that there is a loss of information, because the information provided by 1280 by 720 pixels, which basically an image with higher pixel density, is more than the one that has lower density. This can also be observed by looking at the trees in the environment. The shape and the texture are dull when a lower pixel size is considered. This loss of information might result in improper filter selection during training, affecting the accuracies of the model. Early wildfire detection of wildfire contains detection of small fire spot, and thus having higher pixel density is important and necessary. In early wildfire shots, as depicted on the image on the left, flames are not the prominent feature of the image. Thus, segregating filters that result in features of the flame becomes difficult. Some algorithms may even overlook the flame features and characterize some other irrelevant feature to be a flame. This produces errors and false alarms. This is the reason why a study on flames dataset, which is available on IEEE Dataport, only produces around 60% accuracy when tested through a simple CNN algorithm. On the contrary, the image on the right depicts an aerial shot of wildfire that has spread, causing considerable amount of damage and which is hard to control. Algorithms on images like this work effectively as the features of flames and smoke are clearly the prominent features. Thus, to create an algorithm for early wildfire detection becomes a challenge. In this paper, we present a solution utilizing the segmentation technique for wildfire image analysis. The segmentation involves breaking down a high pixel image into several equal-sized pieces, treating them as separate images. This division does not result in information loss, but it can impact the integrity of objects' shape within the image. For instance, the tractor shown in the image, in a complete image, loses its shape integrity when split into two images, because one segmented image has the body of the tractor and the other segmented image has the tires of the tractor. This limitation makes the technique less useful for detecting objects with fixed shapes. However, for amorphous objects like flames, which lack a fixed form, the segmented image approach is very effective. The number of segments created from an image depends on the pixel size of the original image and the desired processing speeds. Smaller pixel sizes lead to faster processing speeds. In this paper, the original image's pixel size is 1280 by 720 and it is segmented into 12 pieces of 320 by 240 pixels each. Segmentation yields two positive outcomes. First, flames become a prominent feature in one of the sub-images, enhancing the algorithm's ability to detect flames and smoke for improved early wildfire detection. This can be seen in one of the segmented wildfire images. Second, processing speeds increase as the pixel size of the input image decreases, resulting in fewer computations compared to using the original image. When implementing this algorithm, a UAV drone with a 720p camera, the recorded feed is in video format. This video feed comprises of frames, which is suitable for classification by the algorithm. A 60 fps 720p camera records 60 frames of 1280 by 720 pixels per second, but not all frames are relevant due to the UAV's motion. Selecting a frame every 20 frames per second reduces computational costs and accelerates processing. This approach also allows time for additional programs on the UAV, such as fire alert signaling processes to send results to authorities for necessary follow-up actions. Now let us move on to the SegNet's architecture. This architecture is based on convolutional neural networks with support vector machine used to draw a hyperplane among the data points with ReLU classifier for convolutions. Successful use of linear support vector machines for binary classifications was performed by many researchers. And ReLU classifier has proven to be much faster at convergence compared to tanh and sigmoid, and hence the ReLU classifier has been used here. The model comprises of 5 layers of convolutions and 2 hidden layers separated by a flattened layer, with one output layer that has a single dense node. First off, we start with an image with RGB channels that translates through 320 by 240 by 3. Remember, this image is a segmented image and not a complete image. This segmented image is then fed forward to the first convolution 2D layer, which has 32 filters and ReLU as the activation function. Then it goes to the first max pool layer. Subsequently, it goes to the second convolution 2D layer with 64 filters, and then one more max pool layer with the pool size of 2 and stride of 2. And then finally, for the fifth layer, we have the third convolution 2D layer, which has 128 filters, and again the activation function is ReLU. Once all these convolutions are done, the result is put into a flattened layer, which means it is flattened into just one particular dimension, and then it is fed forward to the dense layers. The first dense layer and the second dense layer both have 16 units as well as ReLU as its activation function. And then for the output layer, we have one node where L2 regularization technique has also been applied. The most important thing to remember here is this particular SegNet architecture was carefully designed to work in a specific way for accurate drone wildfire detection. I emphasize on the word drone because this particular entire research paper is focused on drones wildfire detection. The process begins with the drone capturing the live video, storing it temporarily in its memory. The video is then split into frames, with only specific frames chosen at regular intervals. This deliberate choice allows the algorithm to have time for other tasks, such as segmentation algorithms, notifying authorities about fires, controlling the drone's flight, integrating with GPS and other sensors, and all of that. A standout feature of this algorithm is its ability to use resources efficiently. By including these additional tasks in the main processing unit on board, it eliminates the need for extra processing units, reducing the weight and cost of surveillance drones in return. This streamlined approach ensures the algorithm works smoothly within the drone's existing setup, making it more efficient without compromising the drone's overall function. From an engineering standpoint, this design not only keeps the drone lightweight but also saves on production costs, which is crucial when deploying many drones to cover large forested areas. The algorithm achieves efficiency by using a simple yet effective architecture with a minimal number of convolutions and dense layers along with the segmentation approach. This strategic balance between computational costs, high detection accuracy, and quick processing speeds is essential. This research paper, the hardware and software were used as follows. The GPU that was used was GTX 1660 Ti Max-Q design. The CPU was AMD Ryzen 9 4900Hs. The softwares that were used in this project, in this research paper, were Python 3.11.4, TensorFlow, and Keras. In the different stages of making this algorithm, we kept a close eye on how well it worked, as shown in this figure. We carefully noted down the accuracy of the model at each stage of improvement. In the beginning, the model had an accuracy of 56.7%, but it had a problem. The training accuracy was 89.2% and the validation accuracy was a bit higher at 59.7% after 15 epochs. This was a classic case of overfitting. To tackle overfitting, we first tried early stopping, but it didn't really solve the problem. Then we added more images to the dataset, and this made a big difference. The training accuracy went up to 97.5%, and the validation accuracy rose to 76.1% with these changes. The model's test accuracy tested with 441 images went up from 56.7% to 71.8%. Seeing the need for an even better solution, we introduced L2 norm regularization. This technique helped refine the model by adjusting its weights and reducing biases towards certain features. This had a big impact, and the training accuracy increased to 99.6%, with the validation accuracy at 99.3%. Because of this adjustment, the model's test accuracy on 441 images went up significantly to 98.2%. By carefully using these techniques like early stopping, augmented data, and L2 norm regularization, we created a well-tuned model. By addressing overfitting and improving its ability to understand different situations, the algorithm achieved an accuracy that shows it's effective and reliable, making it a strong tool for wildfire detection. In the further tables, we see the developmental stages of the model. Various configurations of convolution layers ranging from 5 to 11 layers and dense layers ranging from 1 to 3 layers were systematically tested. Prioritizing the computational efficiency, a balance was sought between the model speed and accuracy. Initial experiments with 5 convolution layers and 1 dense layer yielded a suboptimal accuracy of 54.71%, while an extensive configuration of 11 convolution layers and 3 dense layers resulted in a lower accuracy of 39.1%. The optimal compromise between accuracy and processing speed emerged with a configuration of 5 convolution layers and 2 dense layers, achieving an impressive 98.18% accuracy and the processing time of 240.375 milliseconds, as highlighted by the green mark. This careful exploration of model architecture during development ensures a harmonious blend of computational efficiency and accuracy in the proposed research. To better understand the effectiveness of this segmentation approach, the results were compared with 2 other algorithms. These algorithms are GoogleNet and AlexNet. The 2 graphs shown over here are of the proposed SegNet. With train accuracy of 99.6%, validation accuracy of 99.3%, and test accuracy of 98.2%, with 3 into 10 to the power minus 4 train loss and validation loss of 4 into 10 to the power minus 4. Similarly, these graphs show AlexNet achieved model accuracy of 100%, test accuracy of 92.2%, and validation accuracy of 91.3%. And moving on to the GoogleNet, this model achieved a train accuracy of 99.9%, test accuracy of 76.8%, and validation accuracy of 77.5%. The recorded losses for training and validation were high at 0.24 and 10.629 respectively. One of the main points of focus for this research was to reduce processing times, along with the use of minimal computational power. The processing speeds for segmentation approach were observed and recorded at the stage of hyperparameter tuning and selection of number of convolutional and dense layers. For the segmented approach, single batch of 32 segmented images took an average of 641 milliseconds. Thus, in segmented approach, a complete image of 1280 by 720 pixel resolution was passed through the neural network within 240.375 milliseconds. The processing speeds of segmented approach, GoogleNet and AlexNet were also compared for better understanding, as shown in the figure, as shown in the table. As all the convolution layers are interconnected in GoogleNet in the form of an inception block, which results in higher number of computations, GoogleNet architecture was found to be the slowest at 1.487 seconds. AlexNet performed better than GoogleNet, as it was observed to be faster at 661.54 milliseconds. The times mentioned are the average time observed for one complete image over 10 trials. Moving on forward, these are few of the performance metrics for better understanding of the SegNet architecture. For a batch of 441 images that were tested, we had 235 true positives, 198 true negatives, 5 false positives, and 3 false negatives, which yielded the following: false positive rates, false negative rates, true negative rates, recall, accuracy, and precision, as shown on this slide. Moving on forward, let us look at the SegNet video demonstration. In conclusion, this research tackles crucial issues in wildfire detection by prioritizing improved time resolution and processing speeds while maintaining high accuracy. Utilizing convolutional neural networks, the study introduces SegNet, a novel method breaking down high-resolution images into manageable segments for swift processing without compromising accuracy. The research carefully navigates the challenge of feature reduction, applying techniques like early stopping, data augmentation, and L2 norm regularization to refine the algorithm's capabilities and mitigate overfitting. The final model achieves an impressive 98.2% accuracy on a test dataset of 441 images, surpassing established algorithms like GoogleNet and AlexNet. The segmentation approach not only exhibits superior accuracy but also remarkable processing speeds, handling a complete 1280 by 720 pixel image in just 240.37 milliseconds. The research emphasizes the algorithm's integration into UAV drone systems, optimizing resource utilization and minimizing costs. In summary, this research not only introduces an innovative segmentation approach for wildfire detection but also presents a comprehensive framework addressing critical challenges in real-time processing, contributing significantly to the advancement of wildfire surveillance systems. All in all, SegNet is not just used for wildfire detection but can also be used for other objects detection that are amorphous in nature, and this provides a significant pathway towards detection of amorphous objects. This video comes to an end, and thank you very much. Special thanks to my supervising professor, Professor Hashim, as well as the professors in the review committee of the Department of Mechanical and Aerospace Engineering of Carleton University. Thank you very much for allowing me, for letting me pursue my passion. And special thanks to everyone who had the patience to watch this video through. Thank you very much and have a nice day.